Good morning, folks. How are you today? We just finished 4 labs this week, so I wanted to talk to you about it. I've gone through all of the surveys individually myself. I'm pleased to tell you that 80% or more of you responded positively to all the questions. I want to give an overview of what we learned in labs 1, 2, 3, 4. And of course, each of the labs had their own individual objectives, but here are the big things that we learned. So in lab 1, we focused on Fiji image analysis and Brinell hardness testing. So you learned Fiji image analysis software and you learned Brinell hardness testing. Then in lab 2, we gave you an overview of strengthening mechanisms and it focused on tensor testing. So you learned about various force strengthening mechanisms. You learned tensor testing, also superficial Rockwell hardness testing, and you learned how strengthening changes tensile properties and hardness. Then in lab 3, we focused on cold working and annealing and Rockwell hardness testing. You found out that tensile properties can be customized by cold working and annealing, and you learned much more about Rockwell hardness testing, both B and C scales. Then lab 4, we focused on tempering of steels and impact testing. And in this last lab, you learned about Charpy and IZOD impact testing and learned about ductile to brittle transition, which is quite unique in steels. So then the overall question number 9 on the surveys, I have only results from surveys 1, 2, and 3 so far. The response successful, which was A, successful but needs minor improvements. 81% or more of you responded these two options for each of the 3 labs. Then on question 10, there was open feedback and I want to respond to it. Now, my major objectives in this course have been that each of you get hands-on experience. So therefore, I had each of you do as much hardness testing as I could with the class size. And again, I want you to really participate and volunteer in the lab activities. That's the only way you can get hands-on experience. Now, there were a couple of comments about that we collect experimental data, but we don't use it. Of course, you can understand that for demo slides, I have to use data to prepare the slides in the first place. And I want also for it to be uniform across all sections. And then as far as assignment data is concerned, you may remember that in lab 1, I had you analyze images of the Brinell indents, right? And you may remember that we had each section collect the images, do the indents, and then the images were scanned by the TA and we had to upload it. And it was really quite a bit of overload because we had to do this all in the same week, one after the other. And in any case, collected data is similar to demo data you would have seen. Um, it may be not very different. And the third thing is sometimes in some sections, in some experiments, we may have problems and we may not collect the data. So that is why one of the reasons my assignment data is also not the one that you collected in the lab, but it is very similar. So I want to make sure that for your data, you have clean data for meaningful analysis. Then one of the other comment was that the labs are not synchronized with 305 lectures. So you can see that it is impossible to synchronize it with 305 content. For instance, right in the first lab, you worked with mild steel. Now to talk more about mild steel, your lecture covers it in something like weeks 9 through 10. You probably covered it last week. Then we talked about brasses. Brass would be probably covered around week 12 in your 305. So you can see it is very difficult to synchronize it with the 305 content lectures. Instead, I hope that the labs are helping you learn the lecture material instead. So in lab one, what did you learn? Fiji image analysis and then Brinell hardness testing. And what we did was, this was our formula for Brinell hardness number. I hope some of you realize that the bottom part was just the diameter of the indenter times the depth of the indent. And this portion is the depth of the indent. You use this also for finding the depth of your Rockwell B indentation. Okay. So we could have used Brinell 10x microscope, whose resolution is 0.01 millimeter or 10 microns or so. Instead, what we did was we took a 2400 dpi scanner image, which has a resolution of 11 microns, which is comparable. And 10 micron resolution implies that we could get Brinell hardness number within plus minus 1 in the range of the diameters of indentations we had in lab 1. So these are the key ideas that you learned in lab 1. And what did we find out? We did our demo on rolled steel, which had a Brinell hardness number, nominal, specified by the vendor of 166. Then for the lab 1 assignment, you used a 6061 aluminum magnesium alloy. So again, notice we are introducing you to quite a few different materials. And this is a precipitation hardenable alloy, and you're going to see a similar or the same one in the next lab. So these were the things we found out. We found out that average BHN calculated from D average was 165. Maximum and minimum were 169 to 161. So our measurement uncertainty is plus minus 4, half of this range. Same thing here, half of this range. So notice our average BHN that we found was within vendor specifications. The instrument resolution is plus minus 1, as we just discussed. Our measurement uncertainty for both is plus minus 4. So we find that our instrument resolution is less than measurement uncertainty. And that is what it should be. Of course, if we found that instrument resolution was greater than measurement uncertainty, then if we want to differentiate our measurements, we need to select a higher resolution instrument. So in our case, for instance, we used a 2400 dpi scanner. We could have used instead a 9600 dpi scanner to improve our resolution, right? Okay, so let's see what we did in second lab. In second lab, which was on strengthening mechanisms and tensile testing, I described that there are 4 strengthening mechanisms. So the first one is solid solution, where we dissolve solute atoms that act as barriers to dislocation motion. The barriers to dislocation motion is what strengthens our material. So for example, we dissolve carbon in iron to make steel. So of course, this you have just learned probably in last 2 weeks in terms of talking about steels. Then the second mechanism is strain or work hardening. We use other synonymous terms as cold working or plastic deformation. So here we increase the dislocation density. And we use this word cold work in all lab 1, lab 2, lab 3. And then we have grain size strengthening, where we change the grain size. We want smaller grain size to strengthen the material. So by cold working and annealing, we can change the grain size. And then finally, we have dispersion strengthening. One of the forms of dispersion strengthening is precipitation hardening. In dispersion strengthening, what we do is we disperse a hard phase in a soft matrix to create barriers to dislocation motion. So for instance, in this lab, we'll be using 6061 alloy, which is precipitation hardenable. In lab 1, you just saw we used 6061 aluminum magnesium. So they can customize or precipitation harden it to whatever the customer wants in terms of hardness. So now in lab 2, based on strengthening mechanisms, what we did tensile testing. So for demo, we had this 1018 steel in two cold work conditions. So we had our first curve, which was skin rolled, and the other one, which was half hard. So you can see we increased the yield strength, we increased the tensile strength. The elastic modulus did not change. And we found out that we cannot strain harden this curve as much as we can the first sample. And of course, in the process, we decrease the toughness. So if you look at area under the two curves, the area under the second curve, green curve, is less than the area under the blue curve. Then for assignment, you looked at aluminum alloy in two conditions. Solution annealed, that means it was single phase, and then it was precipitation hardened through heat treatment. We precipitated a hard phase. So in this case, what we found was when we went from red to green, red was solution annealed, and when we precipitation hardened it, we pretty much increased the strength fivefold, yield strength fivefold, tensile strength also fivefold. Again, elastic modulus did not change. And from the slope of the curve, you can see we can strain harden red much more than we can the green specimen. And again, as far as area under the curve, here it is questionable because our strength increased substantially. So the toughness may have been retained. That means we did not decrease the toughness substantially. Okay, then in lab 3, our focus was really on Rockwell hardness. But through the Rockwell hardness, I want to show you that these calibration specimens, we can customize them to really a very specific hardness through cold working and annealing. Annealing is consisting of recrystallization and grain growth. So through this cold working and annealing, we can control mechanical properties very precisely. So we had these three steel specimens. So we measured hardness Rockwell C, and again you can, and then for assignment you use brass specimens, and again you can see that both the hardnesses are within the vendor specifications. Our instrument resolution is 0.1 for both scales. And again, we find that our instrument resolution is less than the measurement uncertainty in all of these cases. So again, if we wanted instrument resolution, if we found that the instrument resolution was greater than measurement uncertainty, and we want differentiation, then we would need to select a higher resolution instrument. Maybe go to a micro hardness even. Then in lab 4, which you just completed and you're still writing the report, here is what we did. We tested 3 tempered 4140 specimens. So the first thing we found was as we increase the tempering temperature, of course, we expect material to soften. So we found that the hardness decreased. Of course, when the material becomes softer, its toughness increases. So we found toughness to increase. So they have inverse relationship. Then we also compared the room temperature toughness, which is the blue line, to low temperature toughness, which is the red line. We really expected this red line to be flat if our temperature was below the ductile to brittle transition temperature. In our case, we probably could not bring all these three specimens to below their ductile to brittle transition temperature. So what we found was we were somewhere in between. In each case, of course, when we go to lower temperature, you can see toughness decreased. So we know that toughness is decreasing with temperature, but it has not fully transitioned to brittle. Maybe this specimen tempered at 400 did fully transition to being brittle. Then the second set of samples was where we varied the carbon percentage. We had two plain carbon steels, one with low carbon, one with medium amount of carbon. So what we found is as we increase the percentage carbon, we increase hardness. So of course, when we increase the hardness, we will decrease the toughness. So room temperature toughness, we see decreases. And again, this steel, if we go to low temperature, the toughness should be nearly zero. So we expect this red line to be below if we are below both their ductile brittle transition temperatures. Again, we see that as we went to low temperature, the material became less tough in both cases. So it is going toward brittle transition, but it has not become fully brittle as yet because our temperature of the specimen was low, not low enough when it was tested. So you can see we learned a lot of things in these first four labs, all the four mechanical properties. So in lab 5 next week, you're going to learn about phases and their properties in annealed plain carbon steels. So that is going to be our big focus. Along with it, again, we are going to learn about some micro hardness concept. Then in lab 6, that follows, lab 5, you're going to learn about phases and their properties in continuously cooled steels. So you can see this particular material you are probably either just covered or you are going to be covering in next week. So finally, the lab is kind of syncing with the lectures, but in the meantime, you have learned much more in the lab about real engineering materials. So I hope you enjoy the next two labs. Have a great day. Bye.